All right. This is probably going to be our last quote unquote physical lab. I mean, obviously we have a test next week and, our lab period will be used or gobbled up because we have a test next week. And then after that, it's the last week of classes, right? So things are coming to an end fairly quickly. But yeah, let's do induction motors in the lab. And essentially what we're going to try to do, for those of you who've watched the previous two videos, this is a torque versus speed characteristic curve for a NEMA Design B induction motor. And this is what I did in MATLAB. I plotted this out. What we're going to try to do is replicate this to the best of our ability. It may not be perfect, but we're going to try to go ahead and replicate this figure as much as we can, and then do a couple other things about induction motors and see, if they make sense with what we're trying to accomplish. We'll look at some power curves, we'll look at some currents, and then we'll look at some breakdown and starting torque and kind of go from there. So here are all the components that you'll need for the lab. We always have our power supply and our data acquisition. We have an induction motor over here, and it's a 4-pole squirrel cage induction motor. And you can take a look and zoom in a little bit, and you can see some of the characteristics of this particular induction machine, but they're over there. I've also added on this prime mover dynamometer. And the reason why I want that is I want that to actually operate as a load. So if you notice, I'll toggle this switch over to dynamometer mode. So it actually acts like a mechanical load. All right. So let's go ahead and power this up. And you can see it's plus minus DC. And I want it to be a fixed DC. So I'm going to drag that voltage there. And that supply there. And now I have power to my dynamometer, which is good because I want this to operate as an eddy current style dynamometer. So I've got a load there. But I also need to make sure that I power up my induction machine. So I'm going to Y connect this, which means I'm going to drop a neutral on this side. Make it pretty easy, hopefully. And now I'm going to go ahead and power up my squirrel cage induction motor. And what I'm going to do is I'm going to run that off the fixed 120 volt, because if you remember from class, in our last class, we talked about the output torque varies by the square, is proportional to the square of the voltage. And so I really want to just look and see what the effects of load is on an induction machine and not varying voltage. So I'm going to use this fixed 120 208 volt source, not the variable one, because I want to make sure that it has the highest voltage that I can achieve. So I'm also going to want to measure the three-phase power going into the machine. So I'm going to run that into my multimeter and then go over there, and this will be my phase 1. I'm going to do the same thing for phase 2. And the same thing for phase 3. Okay. And again, I ran those through my multimeter so that I can go ahead and start to measure the amount of current draw out of this machine. But I really only care a little bit about current. I really care about power. So I'm going to go ahead and I'm actually going to monitor the voltage. And because I'm looking at the current that goes from the line to the load, which in a Y-connected load, line current and phase current is the same, I'm going to go ahead and measure the phase voltage with terminal 1, because that's going to I1 here. So I want to calculate the power, which means I have to get the phase relationships correct, which means I have to get the phase 1 voltage and the phase 1 current. So by dragging I1 to here, I need to make sure that I grab my voltage here. And then I did the same thing for 2. And the same thing for 3. Now I have all my positives. Now I need my negatives. And so I'm just going to run one neutral over to any one of the phases. And then I'm just going to jump her on to here, because again, these are phase voltages, so they're phase to neutral voltages. And I've got those terms there. So I have almost all of the machine wired up properly. The other thing that I want to do is if you look at the front of the dynamometer, you actually see that this has a torque and a speed output. So I'm actually going to run those analog outputs over to my data acquisition so that I can record those at the same time. So here's my torque output. I run that to terminal 7. You can see it says /T. And then I run speed and RPM to 8, and I run that over there. Now, the only other thing I have to do is make sure that my grounds are tied commonly. So you can see there's a ground here that needs to be tied to this analog ground. And so now I actually have all the machine set up the way that I need to. And just for giggles, I'm going to turn this on and I'm going to watch the rotation. And hopefully you can see it rotating in a clockwise direction as shown there, and it's picking up in speed. If you can't tell, you also see right here, hopefully you can see with my cursor, it shows clockwise CW in a text description. So if you can't make it out, you can actually see that it's clockwise there. Okay.
Now, if we swap two of those terminals, it should go counterclockwise, right?
Yeah, that's one of the lab steps that you'll be doing at the end of lab.
There's one
All
thing
right,
that
so we're feeling pretty good. We can flip off the breaker. And now things seem to be rotating okay. So at this point, I'm ready to start doing the lab, except I need to configure my meters, right? So I'm going to want E1, E2, E3. I don't want E4 because I'm not measuring E4. I want I1, I2, I3, but I don't want I4 because I'm not monitoring it. I also want to enable torque, and I want to calculate and measure RPM. And then I also am going to want to measure power, but because I have all three phases measured correctly, right? I have PQS1, PQS2, PQS3, each one monitoring the individual voltages. I can add those together and I can get the real power. And I'm going to want the imaginary power. Okay. And so I have all my parameters necessary to go ahead and set up to do the lab. So pausing for a moment to make sure everybody is on page or in step with what I'm trying to do. Everybody following along?
Yes.
You can also right click here. You can stop the motor if it's irritating you because it spins down just like it does in lab, right? In lab, if you de-energize it, these motors will spin for quite a while before they actually stop. So you don't, it's not continuing to spin because there's power there. It's continuing to spin because it's got some inertia. So just like it does in the real world, it replicates that. The thing it doesn't replicate is the noise. So if you're in the lab, it gets pretty loud when we're running these things. You had 4 lab groups this morning and all of them are running. You kind of have to shout to be heard because it's just a lot of ambient noise.
What?
Yeah, exactly. Yeah, there's a lot of yelling because I mean it's like walking into an industrial facility. Like there's just a lot of ambient background noise, and it's not ear piercing, but it does make it hard to hear. And over time, you can get hearing issues because of the volume associated with it. Okay. Any questions on that?
Nope.
Okay. So we are on, we've got everything configured. We're using not as shown in figure 3 because we modified it because we have an extra channel. You can use figure 3 if you're limited with meters, but we're not. So we do the full blown one to get the most accurate results. And now we're on step number 5. So we just ran it across the line, so we don't have to worry about the voltage being at 120. We're good to go. So what is the rotation of the squirrel cage induction motor? And then what is the speed of the device? So we're going to flip the switch, and you should be able to answer number 5 once it gets up to speed.
1914.
I hope you're not going that high.
That's what it shows on the display.
Are you seeing my screen?
Yes. Yours is
I get 1775.
yeah, mine is 1914 for
Did you set it on prime mover mode or dynamometer mode?
oh whoops. Oh, there we go.
Because in prime mover, you're driving it at whatever speed it
Right.
wants.
Okay. Yeah, okay. Now I got the same thing. 1775.
Okay.
There.
And Arthur, that brings up a good point. But could you look over here at this diagram and tell me why perhaps the number you gave me was incorrect?
Let's see.
If you can't, it's okay.
Uh
I shouldn't have to zoom in anymore. You should be able to see it from here.
yeah, well you got I don't know.
What type of machine is this?
Oh, yeah, that's not a synchronous machine, it's an induction.
Right, but it's a four-pole
Yeah.
induction machine, right? And
Right.
the synchronous speed of a four-pole machine would be 1800 RPM.
Yeah.
An induction machine cannot operate at synchronous speed. It has to operate at lower than synchronous speed, which means it has to operate at lower than 1800 RPM. And I think the number you gave me was 1900, which would
Yeah.
tell me that it actually wasn't operating as a motor. It was operating as a generator.
Yeah.
So
It was being
yeah,
over.
that, and if you remember our torque versus speed curve, right? If you're running above synchronous speed, the torque goes in the negative direction.
Yeah.
So the question was, is the no load speed almost equal to the speed of the rotating magnetic field? Well, we just said it's supposed to operate at 1800 RPM at synchronous. We're operating at 1775.
It is not.
So say that again.
Uh, is it almost? Yeah, almost 25 RPM off.
Yeah.
Horrible.
To me, that's pretty close, right? This has a pretty low slip. 25 divided by 1800 RPM would be a pretty darn small number, right?
It's not calculus close, but it's close.
It's close. Fair enough. Yep. Okay. So now we can go back over here and just make sure that our torque is going to be set up for the, let's see, the torque meter is enabled, the torque correction function. So we want this corrected. And now we're going to adjust the torque. So the power in the metering window right over here is about 175 watts of nominal output power. How would you go ahead and do that? How would you calculate that? We want to go ahead and do a 175. We don't want to do here, right? Because this is input power. How would you calculate output power?
Oh wow. So we can use the rotation speed.
Keep going.
Oh, Jesus, my notes are all over the place here. I know it's a function of the frequency, the rotational speed, and the magnetic flux, and oh goodness. Let's see. Or we could find out the current that it's producing or consuming and the voltage it's producing and consuming. And
How about right here? Power equals torque times omega. So
right.
torque equals 9,550 times the power in kilowatts divided by the speed, right? So if you want to calculate what the torque needs to be, you take, you want the output power, you take 9.55, multiply that by 175, and then you divide by the speed, right?
Right.
So what we're going to do, now that we have that equation, I'm going to enter that into Excel, so I have the calculation. So this is my torque. So my T, I'll just put equals. It's going to be equal to 9.55 times 175, right? Because if you're not in kilowatts, you have to divide by 1,000 essentially. So that means we have to convert the 975. And then we're going to divide that by our speed, and we'll call that B1. In here, right, we're going to go ahead and have to adjust our speed. so that we get the value that we expect. So I'm going to go ahead and turn on continuous refresh. I'm going to go ahead and my speed is 1775. So my power, my torque. Wait a minute, let me read the lab again just to make sure. So at 1775, my torque in Newton meters should be 0.941. So I toggle this over and it's not doing anything, right? It's basically putting out 0. Now I got to turn that up. But this is a multi-step process, right? You can see it's 0.53, but now my speed has reduced. So I got to go back over here, bring up Excel. And
I was getting a different no-load torque rating. And I don't know if that has to do with a setting or if I did something horribly, horribly wrong here. I was getting 0.776
and
Newton.
is this knob was all the way at 0?
Yes. The manual.
Was it in here that you were getting that number?
Shoot, let me
Because
see.
that's corrected versus non-corrected, right?
Oh, okay. Yeah, I was
Like
actually
this one right here, this number here is
okay.
the corrected value.
And
Okay.
that's still 0. Okay. So you turn, I'm sorry, I must have missed, and I apologize. So I must have missed something here. So
Okay.
you're adjusting this brake knob.
I'm adjusting this dynamometer, this torque control.
Okay.
So I'm increasing that or decreasing that as necessary.
Okay.
So this is actually what it's outputting. This is what it actually is demanding. So you can see I'm not there yet. I need to go a little bit lower. So let me change this to 1734. So 0.963. So I got to go up a little bit. And let me bring that over to here. And I'm just going to do it over here in this window. It's a little easier to see it because both points are displayed. Oop, that's over. Okay, let's try this one. So the speed of operation is 1704. 0.85, so I got to keep increasing. Okay. Let's try this one. Now I'm at 1675. Oops. Wrong spot. And 1.14. So I'm way too high, right? I got 1.465. I'm going to put this on another page just so that I can kind of do it in tandem. And it's very sensitive. Go down. Come on. All right, so this is what I get now. 1.045 and 1717. So let's put in 1717. So for me, this is close enough, right? I'm 1.045 versus 0.97. So I think that that's pretty close, okay? So the question is the nominal output power. This is equal to, right? So this is equal to, if we go back to our calculation that it says the power is going to be equal to 9550. So let's see what the actual power is. So the power is going to be equal to my torque, which is 1.045 in Newton meters. And I'm going to multiply that by my speed, which is here. And then I'm going to divide that by 9.55. So that's the actual watts that I'm producing here, right? That's the actual amount of watts that I have. So this is watts or P out in watts. This is RPM. And this is Newton meters out. So this is T out in Newton meters. All right. So with that information, you should be able to do number 6. Everybody have those data points? We're calculating a P out of just a little more than 175, right? 187.9. That gives us a speed and a corresponding torque. We tried to get to 175, but we're never going to be perfect. So we said that's close enough. Everybody good on step 6?
Think so.
Yeah, I'm good, Paul.
Thanks, Nathan. Rita, Leo?
Yeah, I'm good.
Okay. All right, so now what are we doing when we take this all the way down to minimum? We're giving it a break, right? The motor now is running at its max speed, right? 1775. And there's no real torque on it, right? There's hardly any. And so the current is going to be at its minimum. And the advantage to that is now you can run it and it's cooling itself, right? It's a rotating thing. It's got fins on it that's blowing air across it. So running it under light load conditions like this, the motor is very happy. It's not working hard. Whereas before, we were putting out, 188 watts of equivalent torque. So it was working hard to do that. Now it's running very happy. All right, so now step 7, this is where it's really important. So over here, I really wish that Windows did not auto size. It really makes things difficult. So now I've got my 3 voltages. I got my 3 currents. I've got my torque and my speed. And I also have real power and reactive power for all of those. So I'm going to go ahead and set up a data logger. And then specify that I want that voltage, that current, that torque, that speed. I want real and reactive power. And that should be all the data that it's asking for. It's asking for the line voltage, which I'm just calling it phase voltage. That's fine. I'd like to move this to the end, but it just doesn't, doesn't have that capability. So that's fine. We have our torque in Newton meters there. We have our line current going in here. We have our active power. And this one you can't really tell because it sums the 3, but the only way to tell what that actually is indicating is to bring up the metering window. And you can see that that meter 13 is bringing up real power and 14 is bringing up reactive power. And then lastly, I have my torque and my speed. So at this point, you're going to go ahead. Oops. And back up my metering here. And start varying these parameters. So it says to start recording, right? And go increments of 0.3 Newton meters all the way until we hit 2.1. So I'm going to go ahead and record this one because this is, oops, why did I do it there? So my first one is here. I'm going to hit the record button. Now I'm going to turn this up until I get to 0.631. And again, we're not building a piano, so you do the best you can. Oop. Close enough for me. Hit the record button. 0.931. Close enough. I'm going to keep going, but I'm not at 2.1 yet. So that's close enough, right? Because it would be 1.221. Record. Now 1.5-ish. Yeah, it's very touchy. And if you're trying to get really precise, you can always max zoom this in, and sometimes you get a little more refinement. Sometimes. Try that again. I think that's as best as I'm going to get it. So hit the record button. Now I'm going to do a 1.8 and change. Okay, good enough. And then the last one I'm going to record is 2.1 and change. And record. Okay, so now I'm going to give my machine a break because I'm at 1584 RPM and that much torque. If you look at the nameplate for the induction machine, that's overload. How can I tell that it's overload? Hard to see, but you can tell if you look very closely. It says 1685 RPM, right? That's what it provides full load torque. So if it's 100 RPM less than that, it actually is outputting more than 1685 RPM. How do I know that? Because remember this torque versus speed characteristic, the full load output, the full load torque occurs down over here. That's at close to synchronous speed. I'm actually up over here at a higher value. So that would indicate to me that I've got some problems there. Excuse me. So I'm letting it cool off. Okay. So now, once I'm up to 2.1, then I'm going to let it cool again. Now I'm going to go ahead and try to increment it in 0.1 increments. So again, zoomed way in. That's the only way you can do it. I'm going to very quickly get this up to 2.1, what I had before. Okay. And now I'm going to try to go in 0.1 increments and record some data. So let me record this one. And I want to wait until things stabilize. If I don't let them stabilize, I might get some wonky results. That looks pretty good. Now I'm going to go to 2.3. Okay, that's close enough. Record. 2.4. Give it a second to stabilize. Record. 2.5. Let it stabilize. And you can see this is where it's working really hard. You can see how it's slowing down, but it still seems to be keeping up. So we'll record here, 2.6. Okay. Oops, that's 2.7 side. Let's put that up. Okay, there's 2.6, not 2.7. Okay, that's close enough. Let the speed stabilize. And again, if you were doing this in the real world, we wouldn't be this fine. We'd actually have a little more fine control because we could adjust it a little bit faster with more accuracy if I'm adjusting a knob. But that looks pretty good. Now I'm going to keep going. 2.7-ish. And record once the speed settles down. All right, that's probably pretty good. 2.8. Oops, okay, let it stabilize. Still slowing down. And it's getting to the point where it reaches peak torque, which is the breakdown torque. And at some point, it's going to go ahead and start to, just completely slow down very rapidly. But to me, 1372 doesn't look too bad. But at this point, the motor in real life would be really working hard. You would probably not do it like this for a long period of time. I skipped 2.9 because I can't get there precisely, but let's see if this is actually, if I went too far. It looks like it might be slowing down. I don't know. Doing some pretty big jumps, but it seems to be slowing down. But you see, this is taking a lot longer to stabilize, if it does even stabilize. And it might have been that we've got too much torque on it that we lost it. And it looks like we lost it because, oh, no. Yeah, see how it just keeps slowing down and down and down and down and down. So we might have lost it because we were at 1371 and now we're down to 6 something, whatever it is. So we lost it. We basically went over, let me show you. We were getting close to here, and at that point, we put too much torque, so we're over here. But the problem is it can't maintain that torque. So what is it doing? It's slowing down, and then hopefully it'll be able to get to an equilibrium point. But you can see now it's at 200. It's barely spinning. And if I max it all the way up, that's the best that I can do. So let's see if we can put one more. So I'm going to record that one here. And then I'm going to go back and give it a chance to cool. And I'm going to try again to get one between 2.8 and 2.9. You can see the torque dropped, right? Because at 200 RPM, I didn't have any luck. I didn't have enough capability. So I missed that point. And so just being really, really fine in its control, I might be able to get one more because I want to see that peak rounding, if you will. Okay. So let's try that again. Almost about over here, and we'll give it a second to stabilize. As you can see, the torque is at 2.43. Now I'm going to very carefully turn it up. 2.7, 2.858. Let's see if it can catch itself there. Keep our fingers crossed that it can. We know it's going to be less than 1371 because when we were at 2.827, it was there. But if it's slowing down, you know what I mean? Like you can see the numbers are slowing and they're not increasing or decreasing as fast. It looks like we would have caught it, but we want to give it a second to stabilize. But we're right at the peak of that curve. We're really getting, you know, just impossibly lucky to go ahead and do that. We only went 0.03 more Newton meters. So let's hit the record button. See, 1, 2, 3. Okay, I'll try that. And then we'll try one additional one and then keep our fingers crossed that we can actually make it. This is 2.93, so only 0.08 above. And I'm going to put this one over here. Let's see, is it going to make it? Hard to tell because it's still going down by 1, but it's not super duper slowing down. And sometimes you just miss it and then it actually really starts to drop its speed a lot. So. Oh, let's go. This is just a process of waiting around, right? It's watching paint dry because you're just trying to see that it's stabilizing. It looks like it's going to stabilize because it is slowing down. Moving. If it stays for like 10 seconds, I usually say that that's close enough.
What speed are you at?
I'm at 1,250.
Okay.
But it's slowing down. Is it not? Is my screen not being shared? Can you not see my screen?
No, I just have like 3 windows open on top so I can do it.
Oh, okay. Gotcha.
I'm at 1338 at 2.867.
Yeah, okay. So we were at 2.852 and we got 1351. So you're in the ballpark, but it's still not really stabilizing. It's 12.47. 1246. Let's see if it goes to 1245. We went to 1245. So like we're right at the threshold. And so this is why it's dangerous to record these, because if it doesn't look like it's actually stabilizing at some point, the floor is going to kind of drop out and it'll just drop down to, you know, whatever low speed that it has. But it's back holding on there, right? I mean, it's seemingly like it's trying, but I'm at 2.924 at 1244. I've been there for a bit. Let's see, 5, 6.
Oh, yeah, I overshot that just a
Oh.
little.
Yeah, and then it slows down to 200 RPM. This one,
I'm at 2.94, 2.939.
oh, really?
Yeah. Yeah, like you said, it's hard to get the knob exactly, and it's like it's slowly falling. It's like 1220 right now.
Okay. I'll clear out this one because it looks like I'm going to be able to catch this one. I think it's been at 1243 for a long, long time. So I think I'm going to go ahead and take a snapshot by, no, and then I said it, and then it goes down. I thought 1243 was stabilizing it, but it didn't seem to quite stabilize. But it looks like it's not going to really drop off. Excuse me. It's going to drop off the face of the earth. So I'm feeling reasonably confident that we probably caught the very last one, because if we try to turn the knob up any more than that, it's most likely that we're not going to be able to get any result that is actually going to exceed. But we'll record the data point here, and then we'll move on, because again, it's sort of seemingly stabilized. So 5, 4, 3, 2, 1, and we'll record it. All right, so now I'm going to go ahead and try one more and just barely click it and see what happens to the speed. Barely touch it if I can. So that went from 2.924 to 3.06. And let's see the speed, right? It's dropping pretty quickly. Will it stabilize? I don't think it's going to stabilize, because now you can see it jumping bigger and bigger, like it's jumping by 10. It was jumping by 4 at one point, and now it's jumping by 10. So it doesn't look like we were able to catch it. So maybe you all were able to get a higher torque output, but I was unable to do that, because now you can see it's just dropping all the way. So at this point in the real world, what I would do is I'd want to save my motor. And so I'm just going to go ahead and take it all the way off the load.
So it's funny you mentioned it like dropping off, because I had it at the 2.9, 4, and I was waiting for it to stabilize, and of course now all of a sudden it just nosedived. Now it's going, I didn't touch anything, and it just started dropping. Now it's like 800 RPM, 770, and it's just falling.
So you might have had it at a case where you were just at, the point where it was going slow, and then the kind of, like you said, the floor drops out, if you will,
Yeah.
and then you're done. So, all right, so let's export the data, and we'll call it IM Lab data. Okay, so we're going to open the file location. And what we're going to do is in Excel, we are going to create a new file. So first off, we're going to open it, and we're going to open, that's under my downloads file directory. So under, and you got to do it with browse, because it's a TXT file. It's a comma separated file. So under downloads, you can't see it here. So we want to go to text files here. And I said downloads, one of my own desktops. So I'll incorporate this data. And it does comma limited, so it should be all set. And there is our data. Real power, reactive power, speed and RPM, torque. Where is my current though? Oh, current's right here. Okay. So now what I want to do is I want to do an XY scatter plot. I want to do power here, or speed as my x-axis, and this is my y-axis, right, which is the torque output. So I'm going to select these two. And insert an XY scatter. And this data isn't correct because it's showing you this is torque and speed. I want to swap those around. So I'm going to edit that data or select the data. And my X values are my speeds. And my Y values are my torques. Oops, how come it didn't switch? Let me try that again. That's my X data is here. My Y data is here. And there is my torque versus speed characteristic as it compares to what I have here. So you can see it has that, that sort of that characteristic here. It goes up. And then unfortunately, with the limitation of the machine, we were not able to get, a good bunch of points over here. What we were able to do is just kind of get a straight line between here and here. So we couldn't get any of those points in between there. But if you squint really hard, essentially, especially from the breakdown, from the breakdown, the pull-out torque on, it looks pretty close to the curve. Okay. So you should have enough information to answer number 8. And for number 9 to indicate the nominal value. And let me go ahead and turn off the power here because I don't think we need any more data. To get the nominal speed, it's here. You can't really read it all that well, but hopefully you can make out the nominal speed, 1685 RPM, right? That's the nominal speed. And the output power is going to be 200 watts at that speed. So if you remember when we did our first data point, and when we had it, we were trying to get it to about 175 watts, but we were actually at 188, right? So our speed here, it's 180 watts, that's P out. That's less than the 200 watts, the nominal. So the speed should be above the 1670 RPM, which in fact it is. So we expect it to be that way. Okay, so you should be able to answer number 8. What's breakdown and locked rotor torque? Breakdown is the peak value here. Locked rotor is basically when it's spinning at a very low rate of speed. So you should be able to get those values from number 9. Number 10, you should be able to do enough. Does anybody need any help answering number 10? This is a good opportunity for you all to practice working in Excel and creating curves.
Do you want it in Excel or MATLAB?
I would do this in Excel. MATLAB's good for doing calculations, but you've got a bunch of data here to plot. In Excel, it's far easier to do it in Excel than it is in MATLAB, in my personal opinion. So I would only do MATLAB if I had to do a bunch of calculations. But if I'm going to display data, even if I'm displaying MATLAB data, I will export the data from MATLAB and put it into Excel just to make much prettier plots. And that's what I've done in industry. I had to do, over the summer, I had to do some calculations for a utility. And it had a bunch of complex number calculations, and it's like, wow, I can just do this in MATLAB with a while loop pretty easily. And then I had all these data points, and then I just exported all the data points into Excel so I can make really nice looking charts, very professional looking charts. Where in MATLAB, to make them look even remotely professional, would have spent a lot of time with legends and this and that. So it's like I can do that in Excel in an hour, where in MATLAB it would take me all day to get a chart that wouldn't look nearly as nice as I could do in Excel. So that's what my general approach to doing plotting is. Any questions on how to do number 10? Because number 11 is based on number 10. And for number 11, you have the nominal 9 current right here. Oops, don't know what happened. 1.14 is the motor operation, not generator, but motor. So it puts out it draws in 1.14 when it's at its nominal value. And again, we can compare that over to our data point here, and we can look and see what the input power is. If you wanted to calculate just for giggles, so this is something that is nice to do every once in a while too. This here, this is P in, right? So we'll call this P in bars, or we'll call this Q in, I should say. This here is P in, and this is in watts. And over here, let's calculate P out. Well, we had an equation, right? When we said, and this is what we got this from, whatever application, what was it? Google's, whatever their smart system is. So to calculate power, right? That's going to be equal to the torque, which is here, multiplied by the speed here, and we divide that by 9.55, 96655. And that tells me the power, right? So we can go all the way down and we can look at the power output of the machine. And then another thing that I'd like to know is efficiency. What is the efficiency? It's P out divided by P in. So let's go ahead and pull all these down and let's see what our efficiency is. Our efficiency peaks right over here, right? Right at that when that P in is equal to about 220 watts and it outputs 166. So let's compare that to the nameplate. And the nameplate said it's about, well, it actually, that's a power factor, not even efficiency, but you can look and see the efficiency. You can calculate the efficiency, but we can actually compare the power factor, and let's see how that compares to our nameplate. So let's move this down over here. And this is just additional stuff because we're having fun playing with this. So our power factor here is going to be equal to P in, right, divided by, how do we calculate power factor? It's the real power over the total power. So it's the square root of the real power, right? I'm just not selecting that. Oh, it's not selecting it. E2 squared, and then we're going to add to it that one squared, and we'll take the square root of that. So our power factor is pretty bad at first. And let's copy that over. And what do we know? Right at around 200 watts, our power factor gets to be a reasonable number, right? And that's just compares to our nameplate, 0.73, right here. So we're looking pretty consistent to the data we expect. And then it's interesting too, but our power factor starts to improve. The more power we draw out of this thing, our power factor gets to about 0.88, and then it sort of settles out at that value, and then it starts to drop. And under really low conditions, what happens? There's no power out of the machine. But look at the reactive power demand. It is massive. It's a huge number. And so what that tells me is that I'm drawing more reactive power than real power. And so that's indicative of a poor power factor, although it's only 0.8. Why is it so low? It's E18 squared plus F18 squared square rooted. And it's E18. I'm surprised it's such a high amount of power, but okay. Anyway. As you continue to increase load, you can see that the real power increases a little bit, but look at the reactive power. So it looks more and more like an inductor, just like the equivalent circuit. Okay. So let's go back to, let's see. Should be able to answer 11 and 12. Oh, 11 and 12. So let's stop here. And look at 12. 12 should be a piece of cake, right? All you have to do is swap any two leads. So the power's off. So all I have to do is drag this over here and then drag this over here. It was going clockwise. Will it go counterclockwise? Swap it around. And it didn't. How come it didn't swap? Did it not swap it? Let me check. No, it did not swap. Let's try that again. Let's bring this one over here. And this one. Well, let's turn off the machine. Okay, let's turn it off. We'll stop rotation. All right, so this wire over here is coming out of terminal 2. So let's see if I can drag it up. Nope, it's switching it back over. So I'm temporarily going to drag this one over here, and then I'm going to move it around because it keeps defeating me, if you will. So it was going clockwise. Now I swapped 1 and 2, and you can try whichever one you want. The direction should be counterclockwise, which it is. And even the speed is going in a negative direction. You can swap any two leads. It doesn't matter. We swapped 1 and 2, but I can swap 2 and 3. So let's go over here and drop that over here temporarily. We'll move 3 up and then bring that over here. Let me stop the motor, because in the real world, you wouldn't actually energize it when it's still rotating, because you could break it. So let's plug it on, and it was clockwise, counterclockwise. Now it is clockwise. So any two leads, just what we showed in class, right? When we swapped those leads, when we were doing the magnetic fields, when we were doing the rotating magnetic field on the stator, it goes ahead and rotates direction. But if you look at the speed of operation, it still stays 1775. That doesn't change anything. Okay. Questions? Does anybody want my data?
No, I've got mine. I'm just trying to plug it into Excel.
Okay. Does anybody want my data, or do they want to use their own? It's totally up to them.
I was able to get my own data this time, but yeah.
Go ahead.
Yeah, I've got my own too, Paul.
Okay. Well, I will place it in the chat. It's not great, but if anybody wants it in the chat. It's kind of a mess. Oops, there's too many characters, so I guess I can't post it in the chat. I'll post an image of it, and then you can have it if you want to go ahead and check your data versus mine. So I can't send you the numbers, but I can send you an image. Okay. Questions on the lab. So induction motors.
No questions here.
Okay, well, there are no questions. I will pause the recording. Stick around and answer whatever questions you have. And if you have enough information, you're welcome to take off. So I will pause now. Oops, that's not the pause, that's the stop.